You were not graduating.
Okay, let us begin. Welcome, PCS members and friends, to our PCS IBS seminar. Today we have a pleasure of hosting Dr. Bruno Tomasello from University of Kent in UK. And our scientific host today is Alexei, who will introduce our speaker.
Yeah, thank you, Helen. So, we're welcoming Bruno Tomasello. We're going to talk about both crystallized and topological complex rare earth systems today. We'll briefly introduce the speakers. So, Bruno received his PhD in 2015 in the Capital Laboratory in the UK, where he was supervised by Bruno Tomasello, co-supervised by Paolo Castellano. He then moved to Institute Laura Langeron in Grenoble in France, where he continued to work with Team Simon and was a lecturer at the University of Kent afterwards, where he's now a visitor. So his main research interest, as you can infer from the title, is centered around quantum magnetism and theoretical description of the properties of the materials and quite close collaboration with experimentalists. So with this, the screen and the audience is over. Thank you. But let's go for the screen.
Thank you very much for the warm and kind introduction from everybody. I've been here about a week and it's been quite a pleasure. Please bear with me in terms of this presentation because it's the first time that I will be presenting some of the results. And also it's been a while that I haven't discussed some of the other results. So yes, we'll see how we go step by step. I actually wanted to set up a timer because I would like to have this split in two, more or less. So okay, I thought it was okay, so I thought it was useful to start from the outline of the talk, meaning I will just give a brief intro about myself, then talk about rare earth ions in general, why we think these are interesting atoms to look at, especially in complex condensed matter systems. And then this seminar will be divided into two main chunks. One is the role of rare earth in pyrochlores fields. The other one is rare earth in so-called garnets. Okay, there are some bullet points here which I won't go into the details because we will discuss them in the remaining. So bits about personal background. I wanted to show you very simply where I'm originally from, which is down here, the south of Italy, Sicily, more exactly, Catania. This is where we are right now. I thought it was a nice way to see it. And this is basically where I spent, I think still nowadays, most of my life. Here you can see Catania, the seaside, the volcano, the Etna, which maybe some of you know. And basically up to when then I moved abroad for my PhD, I had studied at the University of Catania, where I got my master in theoretical physics eventually. Later on, life abroad, initially moved to Oxfordshire at the ISIS neutron source, sponsored by SEPNet, eventually implicitly by the University of Kent. And I spent a little bit of time at MPI PKS. I was hosted there basically for the end of my PhD. And actually, I have to say, the first time I heard about this institute is when I was at PKS, there I learned about PCS. And then afterwards, for my postdoc, I decided to keep pushing this idea of doing theoretical physics together with experimentalists, and so I moved to Grenoble, where the Institute Laura Langeron is basically the European leading place for neutron scattering studies, and also it's quite known, I would say, international. So before I started, I thought also it was useful to acknowledge research and collaborators. Again, as I said, today we'll be discussing mainly about rare earth pyrochlores and rare earth garnets. I would like to acknowledge especially Castellano, Messer, and Quintanilla, who supervised me during my PhD, And more recently, a lot of theory has been doing with Tim Simon at the ILL. And here is summarized in two main groups, the experimentalists that I've been working with over the last 4 or 5 years, I would say. These are more new collaborations, I would say. I would take the opportunity to acknowledge this new project we have with Alexei Andrianov about edge sharing two-dimensional lattices. And also, I've been involved in this revision of Joseph Chapman at the University of Kent. And I've got some new interdisciplinary projects going on at the university, but again, I won't get into the details of all of this today. So, okay, why rare earth ions as a focus? What I want to summarize in this slide is that rare earth atoms are elements, are something that attract a lot of interest from different areas of technology in general. And what we're going to be concerned with today is indeed a sub-part of the whole series of the rare earth. Here you see them in colors. Here are the lanthanides, basically, namely also the rare earth. And today we'll be talking mainly about terbium, dysprosium, and holmium. And especially the interest is about their magnetism in solid-state systems. And I thought it was a good way to describe where the magnetism comes from, which is basically the 4 f-electrons in the unfilled shell. So this is a common denominator that we have for all of the rare earth atoms. Especially what we'll be concerned about is the fact that because of their strong coupling between the spin and the orbit angular momenta, we will be mainly concerned about their total angular momentum and the fact that indeed this is the good quantum number to describe their Hilbert space. And what we'll be discussing today is that we will always move in a sense within what is called the eigenspaces of the total angular momentum, which is J. And as you can see here in this table, for the different amount of electrons that we have in the subshell F, we do get different type of total angular momenta, which eventually are well described by the Hind's rules. Okay, so diving into the rare earth pyrochlores, basically the main themes would be frustration. In this case, in this context, spin ices, and especially so-called emergent magnetic molecules. Now, as you might guess from the name, spin ice must have something to do with ice. And so I thought this is actually a web page that I found during this weekend, which I thought was having some images showing to us where is placed in the phase diagram of water, where is placed the so-called hexagonal phase, IH, and how are the oxygens arranged in this phase. Okay, you can see that actually the oxygens here are quite ordered. There is no issue with this. So this is actually a crystal of oxygens. However, if we are concerned with the position of the protons, what has been eventually discovered and understood by Pauling is that in the hexagonal phase, this IH phase of ice, there are different ways in which the molecules can arrange. And so here you see represented that 6 different states that correspond to a same energetic ground state. Okay, so the characteristic of this hexagonal phase of water, ice, is that the oxygens are well arranged. However, the bonds of these, the bonds that are due to these protons, they can arrange in different ways. And here you can count them in terms of being 2 of them near or 2 of them far for a given oxygen of interest. Okay, you can see that all of these configurations, they feature this specific characteristic. So 6 different configurations with the same energy.
Are there other versions of ice crystals where this degeneracy doesn't occur, or is it Typically,
That's a good question. I'm not aware. I noticed actually that whenever we discuss about these subjects, we always go the best into the specificity of saying that it's the hexagonal phase. But I'm not that knowledgeable in that sense. I wouldn't know. Clearly here we see there are different solid phases. So I wouldn't be surprised if some of them actually do order more properly. I mean, we're talking about molecules.
Sorry, what's maybe getting the difference between the first thing? Aren't just can you see it?
the hydrogens, the hydrogens and
The
their bonds are
orientation of the center.
So basically,
Okay, yeah, but let's say you have
the rule that, of course, here you're not seeing some of them, right?
Yeah.
These
Yeah.
eventually are connected.
Because they
to
are
others.
out.
Yeah.
I see.
Or because it's a regular structure.
But in general, the rule is that if you focus at this tetrahedron,
Mhm.
which is not a coincidence, you end up seeing that there is a total of 4 protons inside, and only 2 of them are nearby the center, and the other 2 are further away. So this was the first time that I think what we nowadays call frustration. But where is the connection with ice? The connection is frustration. There was, I think, the first instance in which frustration was implicitly realized. So to understand it in very simple terms, I thought it was useful to, consider a one-dimensional lattice and think about placing one spin. Here we're talking about spins which are nearest neighbor antiferromagnetically coupled. And so as soon as we choose the position, the configuration of one at the beginning, because of their antiferromagnetic coupling, we only find one specific ground state. Okay? So one state, this is done, system is happy. The similar happened for a square lattice. So you fix one at the beginning, then the others follow naturally. However, as many possibly of you have seen in the past, this is not the case for an equilateral triangle, in which if we fix the first one to be pointing up, the second one to be pointing down, the third one we say remains frustrated. With this, of course.
But when you split the order of the spin, you also have to graph state, right?
Sorry?
If you flip order of the spin at the same time, have another graph state.
Here.
Yeah.
Yeah. That's why I said like the easy way to understand this, that would be a broken symmetry state.
Yeah, easy to.
But the easy way to understand this is that you think about fixing one. So you fix one and then the whole thing is known. While in this case, you fix one and you still have a degree of uncertainty. Okay, so this is the comparison I wanted to.
In the quantum mechanism, 120 degree.
Correct. Yes, yeah, definitely. Indeed, you're right. I forgot to emphasize that this at the moment is classical easing type of coupling. Okay, easing meaning that it's uniaxial, they can only point in a direction, and it's classical meaning that otherwise quantum fluctuations would make you stay in a superposition of the field. Okay, so frustration prevents minimizing all points interaction simultaneously. This is basically the definition of what we understand as frustration. Now, in spin ices, for some reason, there's a little bit of delay every time. In spin ices, basically, we're talking about 3-dimensional lattices. And what we'll be focusing on today, because we talk about spin ices, which are pyrochlores, is actually a unit of frustration that is a tetrahedron. If you think about it, it's the simplest 3-dimensional extension of what we saw earlier, a triangle. You stack the triangles together and you get a 3D equivalent of a triangle. And so, modulo some further details that we could discuss, I thought it was useful to jump directly in what is the spin ice state, which you can see here as represented in terms of now having, again, classical easing spins, ferromagnetically coupled now, with local easing axis anisotropies, and obeying this 2-into-out rule. Okay. So if you think about this 2-into-out, and then you compute how many possible configurations there are, you do see that there is a total of 6. And so it should become more or less evident that this is why it's called spin ice, right? Because we have exactly the same 6. And this could be mapped exactly to that type of disorder that we had in those parts. Of course, if there are questions, feel free to interrupt at any time. Now, this is something I've done here. I thought it's something I wanted to do for a while, but I thought it was useful, especially for the graduate students in the audience. I thought, okay, let's take a little cluster of this pyrochlore structure, and let's see how many configurations there are for a 25-spin system. All of these configurations are obeying this local and yet globally correlated constraints of 2-into-out rules. Okay? I say local because we focus on a tetrahedron. I say globally correlated because, of course, every tetrahedron will impose that condition of the neighboring ones, and this correlation will propagate throughout the whole lattice, and it, of course, will create constraints. This is what people call kinematic constraints, and the fact that there are some fluctuations allowed, the system is paramagnetic because there is no magnetization, but it's not a disordered paramagnet, it's a correlated paramagnet. And so I thought it was cute to see the possible configurations, and unless I have a bug on my model, your eyes should perceive that basically when you span from 0 to those 6,561, these 2-into-out rules are always satisfied. So this is it should give you an amount of the degeneracy that we're talking about. Okay, it should give you an idea. This is what we mean by macroscopic degeneracy, because if I take this lattice and I expand it in 3D, then my degeneracy increases, and this is why we need, I guess, good computers to make calculations about larger and more realistic clusters.
Here you use open boundary conditions. I mean, the ones at the edges are not connected.
Exactly. Indeed, what I witnessed is that if you eventually violate, at least for example, in one case, you would still get, if you get one violation of one tetrahedron, you will get the same number of configuration because, of course, the boundaries are free to explore what they want.
So the difference between a frustrated system and the system that has, let's say, a genuine degenerate ground state is that here the degeneracy is macroscopic, explode with, so it's a bit qualitative in some sense, right? The difference.
I would say it's quantitative in terms of the fact that you can estimate it. This is what we're going to see now.
Yeah, but
because basically in a system in which you have degeneracy but only of a few states, you wouldn't necessarily see a difference with a given size.
I see. Okay, here is scale with the system size. In the other it doesn't. Okay, got it.
At least to the best of my understanding.
How does it scale?
There is an equation that I didn't write. I know that it's at the best it's an approximation anyway. That's why I didn't think it was worth writing. I can't recall right now. But literally there was a seminar of Michel Gingras where he was explaining the origin of this, but the details are subtle. He was quoting some people that calculated it, but anyway, it's an approximation as far as I understand.
I remember correctly something like 2 to the 2
Yes, but there's a factor there.
So not 2 to the n, but 2 to the 2 or 3 n.
No, 2 to the n is the total states. Essentially, if I remember correctly.
2/3, it's because it should be 6 possible over the total, which is 16, I think, for the journal.
Yeah.
And then you get, yes. Yeah, but there is a prefactor, which is the one whose details I didn't understand how they were accounted for. So going back to in a sense, to the aim of today's talk, what I wanted to emphasize is that in a real material, all of these so-called spins are actually corresponding to magnetic moments due to rarefy. Okay. This is where we're going today, in a sense, as a discussion. Okay, so for stretching spinous materials, the materials are actually, the first ones discovered are these two, holmium titanate and dysprosium titanate. So you may recognize that we're starting to see the rare earth ions here. I shall refer to them a few times as HTO and DTO. This is how some people do to be a bit more rapid. And here what you see is our pyrochlore lattice. Again, here realizes the 2-into-out rule. And this is the first signature of the frustration, where you see that this system, when taken, when we measure the spin entropy, magnetic entropy, at very low temperatures, you get this saturation here at a finite value. So when people started to discuss about this, they were claiming, they were saying that this could be a violation of the third thermodynamic principle, meaning that the fact that there is this residual entropy is defeating our understanding about physics.
And how is it measured?
This is measured by specific heat measurements, and what they've done was integrating basically the area contained by the specific heat. And here, yes, I thought it was worth showing that this range of temperatures is the one at which is well established that we have a so-called spin ice phase in this type of materials. So this behavior eventually was, after some years and some theoretical effort, was well understood and described mainly by, again, what I mentioned earlier, anising paramagnetic effective coupling between Earth's neighbors. And eventually it was pointed out that because these magnetic moments sitting at these lattices actually originate from Earth ions, which have quite some large magnetic dipole, it came out that long-range dipolar interactions should be taken into account as well. So eventually there was a whole field of research that investigated how it was possible for these interactions to not disrupt the frustration.
I question, 근데 consider the symmetry. This Ising type interaction is not they are off-diagonal exchange effect also in the S plus S minus, right?
Right. So the here there are no off-diagonal. Yeah, this is just purely. Yes, my work I did. Yeah, that's yes, that's a good assist. Yes, but that work didn't modify the Hamiltonian at this level. Okay. What I wanted to say here is that at this stage, every spin is to be thought of as just very fixed in this either this configuration or the opposite. And the next important experimental relevance of this spin ice state was the neutron scatter structure factor that was measured by Tom Penner and collaborators, in which these specific features were observed. Okay, so the point is very simple. When we do neutron scattering, if the system orders, we observe so-called magnetic brackets, okay, which are very sharp features. You can see them very neatly. Because the system is disordered, we don't expect any such brackets. However, because it's correlated and disordered at the same time, so meaning the disorder is not just pure randomness, there were some preliminary studies that were shown that some signature of this should be able. And the signature are these pinch points. Okay? And I haven't asked anyone ever, but I think they're called pinch points because you pinch there. Okay, that's why you see in those points, your correlations are showing a specific pattern. And then, in a sense, let me say, boom, the next hot subject of spin ice materials was that it was shown by Casanova, Messer, and Sondi that if you violate these two in-to-out constraints, your effective picture could be described in terms of emergent quasi-particles that eventually was proposed. They behave like effective magnetic monopoles. So what I'm showing here is that this is the spin ice Hamiltonian in terms of the Ising degrees of freedom. And eventually they mapped, so what you can see here is that, so here we have two in, two out, two in, two out. And here what you do, you flip the central spin, and so you have 3 in, 1 out, and 3 out, 1 in. So this is sort of creating your local excitation. The point is that simply we know that the local excitation has to be due to one spin flip. This we know, because it's a spin system. However, what wasn't obvious, I think, before people thought intensely about this is that when you do this spin flip, the way this excitation propagates, given the constraints, is not as simple as a typical spin wave. A spin wave will propagate in a way in which you get the magnons, and your spin waves are propagating through the lattice, and you do your dispersion relations and all that. In this case, it's a bit more subtle because given the discrete nature of this classical excitation, basically it was shown that the dynamics are a bit more puzzling. And so the question when I joined this community was basically, how do these monopoles hop around? How do they move? And the question was simply posed in terms of the fact that if this easing anisotropy is so strong and the system is purely classical, how are these excitation actually going across the lattice? And so what we proposed was that because monopoles have to hop in terms of spin flips, we thought of using a microscopic approach to study the way the magnetic dipoles, and therefore the rare earth ions, here where comes the point, can provide a quantitative answer to understand how it is possible for this large magnetic moment, which is classical, to actually undergo a transition to the other side. And so, as it was suggested earlier, the point is that behind this one easing degree of freedom, there is actually a complex Hamiltonian, which is described in terms of these operators called Stevens operators, and they are a function of the angular momentum operators. Okay? What it means in this case is that our Hilbert space, in the case of holmium, because holmium has a J equal 8, our Hilbert space will have an operator of dimension 2J plus 1 times 2J plus 1, so meaning 16 by 16 matrices. So from a quantum mechanical point of view, it's easy to diagonalize, but at the same time, it starts to be consistent. That's interesting. It starts to be consistently interesting in terms of having quite a sizable Hilbert space with correlations. And so what I want to emphasize here is that we see here the oxygens around a central holmium ion, and these are the objects, the atoms that eventually provide these effective fields that will help us in having these off-diagonal terms that we were referring to earlier. This is where the fluctuations, in a sense, start to come from. So the take-home message, so at least I've got the take-home message from today, is that in a sense, all of the physics I've been dealing with can be understood, at least in an intuitive way, in this manner. You have a generic Hamiltonian, which is described in terms of a main Hamiltonian, which is known. Maybe what's a bit unusual in my approach is that this is truly known thanks to experiments, meaning that we know the way the Hamiltonian can be described, this crystal field Hamiltonian, this is our crystal field Hamiltonian. But the actual good parameters we take from the experiments. And then we infer what are the interesting perturbations to understand the dynamics by studying theoretical systems. So in a sense, I wanted to convey in this slide the summary of the story of theorists who's trying to make good use immediately of experimental data, or as good as I could do. Now, the encouragement in this project came from the fact that indeed the experimental community was suggesting that quantum dynamics could be relevant even if this was a classical system. And this is particularly evident in these three panels, in which these two show AC susceptibility, and this one mu SR. And in all of this, you see that there is a plateau region that is time independent, temperature independent, and which then suggests that if there are no thermal fluctuations occurring, then it might imply that there is some quantum mechanics going on. So I'll try to be a bit faster now. And what I'm going to say here is just that this is your crystal field energy spectrum. So each rare earth ion has this huge jump to the first excited state. And this is why the system is said to be in general classical, because this ground state doublet, this is a doublet, is well isolated from the versatile state.
How to
Sorry? How to overcome it? Yeah, that's exactly the point. So unless at this stage, because of these crystalline charges, these electric fields, you get a partial lifting of the J degeneracy. And this is your partial lift. What we thought about,
how to what did you say is experimental data or
sorry?
what is
This is experimental data. Yes. This is measured with neutron scattering.
neutron?
Yes. This they can measure quite clearly. And as I said, eventually you have your crystal field Hamiltonian written in general terms. You write your code, you put your parameters from the literature, you get exactly that type of stuff.
So what are the dashed lines and the solid lines?
Solid lines are doublets, dashed lines are singlets. Because this is a non-Kramer system, then you can have singlets because basically, yes, because of time reversal problem. If it was a Kramer's, you will have only doublets. Now, the one thing I want to emphasize is that in order to make transitions between these two, you need an effective transverse perturbation. And this is eventually what we're going to refer to today. It's a magnetic field. So what we studied was basically a rare earth ion, which now here you see from the top. These are the oxygens around it, making this oxygen cage. And what we studied was the effect of a transverse field. So as I said, here you see it from the top. And this field is here shown in terms of increasing in strength up to enormously crazy strength.
You can do that.
Huh?
You can do
No one can do that. Well, I have, there are some interesting points about this.
I
This is just a preliminary, sorry?
how to determine over the G tensor.
Well, the G tensor is it's implicit in all of this. So you don't need a G tensor at this stage because you're treating it quantum mechanics. You get your G tensor as extraction from this diagonalization. Okay. What I think this could partially answer is the fact that what's been shown here is just for Zeeman type of couple. Okay, so I'm not going to show the details of the exchange of corrections we've done, but eventually it's thanks to exchange that you do get in a region in which this can be perturbative.
I did consider you only consider the spin model or you consider the real electro F2 orbital state.
What you do is you take your J angular momentum.
J angular
Yes.
F
No, because that's the point. That's why I showed at the beginning that the main Hamiltonian is the crystal field. Because that J is well coupled, the crystal field is so strong, and everything else will be just a perturbation. So you're not going to remove the electrons, you're not going to change your J at this type of perturbation.
Firstly, you optimize the spectral field parameter.
You can optimize them, yes, but for us, the interest was in the dynamics of this system. And so eventually we derived these laws. We understood that the two systems, the spin ices had different behavior in terms of the splitting that regulates these time scales. We obtained an analytical expression by perturbation theory. And so in a sense, we were already able to tell for a given perturbation, what would be the splitting that you expect at a given value of an effective field. And we could distinguish the different ranges of interest. Up to here, basically, holmium titanate is quadratic, and up to here, dysprosium is cubic. And the one other thing that I thought it was worth showing is that this is accounting for the response of the Z, okay, the easing response of the magnetization when you are applying your field transfer. And this gives you an idea of how anisotropic the response is. Because you apply a field along the transverse direction, and your spin is actually responding just by going up or down, up or down. And this is how you start to see in terms of magnetostatics, how some angles would make you point in a direction rather than the other. And so then the point was, where do these fields come from? Okay? And this is where we went back to these cluster calculations. So what you see here is our pyrochlore lattice. And there is no spin here shown because what I would like you to focus on is just that there is an absence of monopoles. Okay? All of the possible configurations we've seen before, we explore them all. What I'm trying to convey as an idea is that all of their possible fields are represented here. Okay, this is the probability, these are the histograms. This is the transverse component, transverse to the easing axis, so I would be pointing this way. And this is the longitudinal component. Longitudinal means along this way. So no monopole and everything is quite longitudinal. You insert one defect and still everything stays quite with a strong longitudinal component. Longitudinal means that whenever it's longitudinal, the spin is going to stay fixed, it won't fluctuate. And then you just let this object hop of one side and you get this huge suppression of the longitudinal component, and you're left with this transverse one, which is double peak. And this is where we thought nice and interesting, because it was showing evidence in a sense that whenever there is a monopole nearby, there is an internal fluctuation from the system that is going to happen, and which is going to let this spin fluctuate, so to help this monopole to go across.
Question.
Yeah.
So, in this case, look like you have the magnetic field induced by the monopole on the spin that you consider, right?
Well, by the monopole implicitly, meaning that it's due to these surrounding dipoles.
Yes. So,
And what we notice is that some configurations eventually do feature something interesting with respect to the model that we were using. Because again, the point is that we were investigating initially the response of a single ion with respect to fictitiously applied fields. Now the fields are no longer fictitious. Now the fields are due to this mean field approximation, if you wish, in which you neglect this central one, and you take into account all of these dipolar fields long range converging into the center.
and with the appearance of this monopole,
With
the appearance of this monopole.
Yeah.
Okay, so basically, this thing is the result of the field here. You calculate by minimize the energy or something.
At the moment, to be honest with you, I think this is something I was mentioning when we discussed. This is taking them into account, all of them.
All of them.
Okay, so that's why it's even more striking, because people had done Monte Carlo, and so there was an implicit selection of certain energies, but this is purely geometrical.
So
like all of the possible configurations, they give you this type of pattern.
okay, so basically you sum over the own configuration with the assumption that the monopole appear at some point.
Exactly.
Okay,
Yeah.
good.
Exactly.
You not consider exchanging.
Exchange at this moment, the discussion, no, but we can talk about
Here.
Yeah.
Because spin is
exchange
matter.
is very complex in this system, and I'd be very happy to talk about exchange in a separate instance, because it's a truly microscopic calculation of rare earth ions that have many electrons. It's interesting but involved.
So the calculations that you did, they were with perturbation.
The calculation with perturbation theory is in terms of understanding the response of this crystal free Hamiltonian to perturbations. What I'm showing here, these are just classical dipolar fields. Okay, so these actually, yes, this is giving to me the field to use in the perturbation.
I also asked a question. I suppose there was a question about if you have a monopole nearby this central spin, you have additional Weiss field, if you can say it, from the exchange interaction. And what is and here you show us the dipolar field.
Yes.
And what is the effect of this Weiss field? It is negligible or?
So the exchange fields are not negligible. They are of the same order of magnitude. However, what I'm trying to say here is that after we've done a thorough work with the exchange, we understood that what we were seeing already here at this sense, at this level, was symmetrically and intuitively correct. So the exchange, in a sense, it was very challenging as a calculation. As a theorist, I think it gave me some joy that I managed, but it was a huge effort for realizing something that, especially for classical spin ices, is already quite there because of the polar interactions. And by the way, something that I didn't emphasize on earlier is that the ferromagnetic coupling that is giving the frustration of spin ice comes from the dipolar interactions. If the dipolar interactions weren't that strong, the exchange would actually make the spin's points antiferromagnetic. So that's why also I like to tell this story in this sense. I'm afraid I won't be able to go in a lot of details of the other discussion. But nevertheless, what I wanted to say is that what people were curious about, sorry, I'll go back for 1 second, is why do you get this double peak? Why are these two things now separated? Because here the distribution was quite uniform. And why is that there is these two peaked values that are coming out? And so I thought, okay, let's go and look at the simplest case possible. And we consider a pair of tetrahedra, interconnected, of course, and a one monopole sitting there. And let's see what are the configurations. And let's see where is the effective field pointing. Okay, and this is my dipolar field. And you can see that in this configuration, which is having here a monopole and here no monopole, so therefore this is flippable as a spin, you do get this quite neat transverse component. If you then explore another configuration, meaning you let these three spins cycle around the 1, 1, 1, you see that your transverse field stays transverse by moving. And if you keep going, the field vanishes. And this again is something that people have not noticed, meaning that it was always told that any monopole configuration is equivalent to any other monopole configuration. What this simple symmetry analysis showed was that if you consider the interactions that are converging into the center, then you understand that they must cancel out in this type of configurations because these two have the same easy axis and they cancel out because they're opposite. These two have the same easy axis and they cancel out. And these two have the same easy axis and they cancel out. So basically, out of the three possibilities, we know that two have transverse fields and one of them doesn't. So in a sense, that's why the take-home message of our publication was that when you want to study correlated quantum tunneling of spins which relate to monopoles in spin ice, you do get these peaked distributions, both when you consider just the 6 spins being nearest neighbors, and also when you consider the exact case of this enlarged cluster. And eventually, for people who had done calculations, with Monte Carlo, they eventually, I hope, appreciated the fact that there was a microscopic explanation of why that was. So in a sense, the main achievement of this work was that there is a dependence on the local spin correlation of these possible fields, which eventually trigger fluctuations. And therefore, implicitly, the system is having two possible timescales. We call them one tau fast and the other one tau slow, because depending on the strength of the field, here you can see that this field is lower than that in strength, then of course they will trigger different timescales.
So in some sense, you can propagate in one direction and in another.
Exactly. So I don't have it here, but I have it as a backup slide. We can go back to that later. But yes, that's exactly the point. And in a sense, that point is implicitly summarized here, where we had done the calculation of the possible timescales for the different materials. Here we were doing some suggestion for Praseodymium systems, which are quantum spin ices. However, again, what I would like to emphasize is that you can see the difference in the magnitudes of these timescales.
Which units?
But these are in seconds.
Oh,
Seconds, yeah. And so, yes, this would be microseconds. And so eventually what was used later on by one of the graduate students at Cambridge was to take a Monte Carlo simulation. I'm not an expert at all of Monte Carlo, so I don't know much of the details of this, how it was done. But my understanding was that they considered the so-called standard model of spin ice, in which they used the Hamiltonian that I showed at the beginning, the classic Hamiltonian, and rather than letting the system do its stochastic process by taking into account the fact that this hopping can happen in any direction, they eventually implemented what you were saying earlier. They implemented the fact that every time that there is this monopole position at some point, the possibilities of branches are changing, the directionalities can be different. And so apparently they managed with these simulations to find a solution to two of the open questions, one of which was the behavior of the timescales at low temperatures. Sorry, yes. Here, pardon. Temperatures, low temperatures. So this is the way that timescales that we saw earlier were going very slow and slow as the system was getting cooled. And the other one is here, these black lines, where you can see that this so-called anomalous magnetic noise that was measured with split magnetometers can be eventually interpreted in a better way as opposed to the gray lines, which is what was used so far.
Could you please comment, what is this anomalous magnetic?
My understanding of this is that what the group of I always forget the name, I'm sorry about this. Well, a group in Oxford, let me say, this is a professor that used to be at Cornell before. These experimentalists, they had this idea of saying, okay, this is, again, as I said, this is my interpretation, I might be wrong. This is a paramagnet, but it's a correlated paramagnet. If it was a paramagnet, we will have a signal, noise, which is white noise, which is purely random. If this is a correlated paramagnet, the noise of the magnetic fluctuations would be patterned. There should be a pattern that comes out. So what they did, they had a collaboration with theorists. We eventually did simulations using the Hamiltonian of our classical system. And eventually they showed that the noise that you extract from these experiments can be understood in terms of this population of monopoles which are hopping up. So this is why it's called knots. There is no magnetoacoustic or magnetoelasticity involved in this stage.
So what do you mean by correlation?
What I mean by correlation is the fact that every time that you are positioned somewhere, you can't say exactly how somewhere else that thing is, but you can say it with a sort of probability. While in a system that is uncorrelated, there is no correlation between the parts.
So the group that you mentioned may be Simons David.
Yes, chemostasis. Thanks. Okay. Okay. So let me know how I'm doing the time, because I could stop here and maybe just briefly introduce the next project, just in terms of saying what it's been about.
10 minutes.
Yeah. Okay. I mean, I know that we've had discussions, but it's,
yeah,
I wouldn't want to overlap. Thank you. Okay, so rare earth garnets. Again, rare earth, but here we're talking about garnets. So in a sense, everything that we discussed so far, at least for this type of class of rare garnets that I'm going to overview, this is a system that orders. So we are shifting in a sense of attention from something where there is this randomness to something that is quite ordered. This is the unit cell of a rare earth garnet. What you see here are the so-called hypercagonal lattices. Again, you might tell that I do like triangles because for my pyrochlore we're going to this. And what I'm emphasizing in these images is that this is the full unit cell, oops, sorry, where you see all of the rare earth ions. Here you see one sublattice of the hypercagonal, and here you see the other sublattice. And I'm showing just some of the magnetic anisotropies. These are the rare earth ions dipoles, because I think it's beneficial for our eyes to see a few rather than all of them together. Very simply, these two. And my interest into the garnet started when I went for this postdoc at the ILL. There was especially a PhD student, Rafal Barzinczak, was supervised by Tom Fennell and Jörn Nielsen, and they were interested into measuring. I don't remember who was asking about this crystal field spectrum that I showed earlier, but basically at that time they were interested into measuring with details the spectrum of the single ion of this terbium gallium garnet. That's the way it's called. So what you see here is the representation that Rafal Barzinczak had done of a terbium ion and the oxygen surrounding it. So again, in this case, here you get your crystal field spectrum. And what they were able to do, and apparently this is something that they couldn't do up to some years ago, was to resolve the splitting that is actually present at this level. What you can see here is that they have something where they can see a gap of 0.2 millielectron. So implicitly, you might notice that this is indeed not a true doublet. If there is a splitting, it's actually two singlets very nearby, which is why we call them quasi-doublets. This might look not entirely familiar, but in a sense, if I had gone maybe more details from the last talk, the former one, this could look familiar, meaning that it's exactly the same idea. We have our crystal field Hamiltonian. This Hamiltonian is described in terms of these J operators and Stevens operators. And thanks to the Hamiltonian, we can actually see the type of eigenstates that our system can have. So this is where I would say the theory aspect comes in. Because of course, this decomposition, what it's describing is the type of symmetry of the system. And this point group symmetry is a D2 so-called point group. And this is the decomposition of the state. Very quickly here, what I'm trying to show is that when you study the different positions of the ions with respect to field, you do get very different behavior of the energy levels. And here I wanted to, in a sense, convey the idea that this interest in the garnets for me exploded when I came in contact with this experimentalist, Stefan Gebrax, in dynamics especially, and more recently with the graduate student, Jack, who were interested into another class of garnets, which are called iron garnets, because now you can see that the gallium is replaced with an iron. So they're interested into, is mainly into the so-called spin-Seebeck effect, and they had been doing already a few experiments about terbium iron garnet and gadolinium iron garnet, and they did seem puzzled. I think we're still very puzzled. But basically, as I said, in more general terms of research, their curiosity was about understanding the so-called spin-Seebeck effect. Now, the spin-Seebeck effect is the equivalent of the Seebeck effect. The Seebeck effect is something quite intuitive, actually. You consider a conducting material, and rather than applying a voltage to it, you apply a thermal gradient. So you can see that this part is cold and this one is hot. And the Seebeck effect is about the fact that you apply a thermal gradient, and actually what you get is an electric field, meaning that there is a flow of current going through. And this apparently, I didn't know, to be honest, up to this weekend, but this is used in by NASA and other space, operations in order to unelement these probes that they send into the planets. It's basically making functioning the batteries of these devices. I didn't know, that's why I thought it was very fascinating to discover it. Basically, they place something very hot inside. They do this, they use these thermocouples. So this is a thermocouple, and it's the way, it's basically, you see they have two metals with different Seebeck response. By the way, this video explains it very well. And if you couple these two wires, basically you are conducting electricity just by applying a different temperature. So they put this thing which is very hot and it's decaying very slowly inside. And then they have these arrays of thermocouples all around. And because the outer side is cold, this thing slowly aliments basically the probes that are there. And apparently it's like it's the type of device that has faulted the least in all of their devices, because it doesn't depend on solar panels or anything.
It's a nuclear core or something.
Yeah, basically, yeah, exactly. There is something very hot which is decaying. It's a radioactive, I think it's called a radioactive source. The spin-Seebeck effect, which is something that I personally am still on the way to understand in terms of its full engineering aspects, is something which is trying to do the same, but in terms of spin currents. And you know, there is this field of research which is called spintronics, which is hoping and targeting the interest of trying to get, let me say, get rid of electrons because they heat too much, and try to use, yes, spins and magnons and all of that to propagate information and eventually to propagate energy in our solid state devices. So very briefly,
Does it come together with the normal Seebeck effect of the material, which?
well, this is what I must say I discovered recently, again, by reviewing the literature, is that I think the first observation was actually that you can have a spin Seebeck in which it's still correlated to the Seebeck. Okay, meaning the degrees of freedom of the spin is carried by.
So you have both, you have the spin current
Exactly.
and the charge.
What these people here are interested in, I think, are purely spin transport, which is why it's still relatively.
So you block the charge.
Yes.
Garnet is the insulator.
Garnet is an insulator. So what you see here is that what they're studying are films of gadolinium iron garnet. They do these sandwiches. This is yttrium aluminum garnet, which doesn't have a rare earth true magnetic contribution. And then there are these platinum foils. And all of this, I think it's done so to then construct these devices, which again, I must say, I don't understand fully how they are meant to function in detail. I'm being very honest with this. I looked at these references a few times, but it does look to me a bit more on the engineering side. But basically what they are interested in is to see how with the change of temperature, you can get this voltage of the spin-Seebeck effect to change, okay, to go from positive to negative values and again positive. And what Geprats et al. Investigated is the relationship between this type of signal and the fact that gadolinium iron garnet is known for having a so-called compensation temperature. These are compensated ferrimagnets. It's a way, yes.
Is it longitudinal or the transverse? Yes.
So here we can see it should be transverse because it's applied like this. I think what they do is basically they play in a very nice way. They play in all sort of ways with applying fields perpendicular and then study the different type of coupling that you can have. And eventually measure always the voltage in the same context.
So you have conducting plane and you have insulating magnets.
Exactly.
How you introduce interaction with them?
So this is, I think, one of the main points. I'm not an expert on this, but I understand that what you see here represented is that there is this idea that you are injecting a spin current through this different ranges.
But you cannot inject electrons.
No, exactly. That's why.
There's sort of exchange or
Exactly.
something, interaction.
This is where I hope, as a theorist, to get more involved at some point. Because at the moment, I'm studying just the microscopic aspects.
I continue in the spin current or magnon chain. It's our magnon.
What they are studying with neutrons is the magnon propagation. And the aim of that is to understand how these magnons can inject a spin current in the remaining part of the junction. Okay. Forgive me if this might not be entirely correct. As I said, I dive into specific aspects of research. I don't necessarily understand the full large scope of this. Let me know if I have to stop, by the way, because I think we are done with time. The one thing maybe that I just wanted to mention here is that these materials were already a point of interest for NEM and co-workers, So it was already known at that time that they had this so-called compensation temperature. And I just wanted to leave you with this very simple explanation here of what the compensation temperature is about. It's the fact that these systems, when we look at them from the 1-1-1 perspective, here you can see the rare earth ions are the red ones, and the blue and the gray are the two sublattices of the ions. Now, all of these materials have, at around 500 Kelvin, they have a very magnetic transition. And below that, what happens at this so-called compensation temperature is that the magnetism of the Earth, because now this doublet starts to have a contribution, which is anisotropic, the magnetism of these ones starts to matter. And that's why at some point there is a temperature specifically in which the two quantities, the two magnetic contributions, they compensate with each other. Okay? So all of this field of research is basically trying to understand how materials with compensation temperature, they can be useful for spintronic applications. So I will skip the details of what I've been doing. But in essence, yes, I just wanted to say that thanks to our understanding of the local environment of these rare ions, we proposed a simple model. It's actually an effective one-dimensional lattice, so we got rid of all of the complexity of the system. And we proposed something which is just showing how the competition between the local anisotropy, the coupling between the Earth and one of the sublattices of the iron, and the coupling between the two types of irons that you have, how all of this is enough to give you insightful
I
features.
You consider the single ion entropy of layers or both? Only consider layers?
So we consider the entrance, sorry, you said the anisotropy, or you entropy, what did you say?
Entropy of iron.
Anisotropy. No.
My point is that K is energy of what element?
Yes, it's an energy. Yeah, this is the Hamiltonian.
But what element is it? You consider iron and other elements here.
This is the rare earth. Sorry.
Rare earth.
Yes.
This
is the anisotropy is only on the rare earth.
But even in 3D transition metal is
energy
is possible, but a little small.
Yes, totally. But the literature so far acknowledges the degrees of anisotropy in the irons to be negligible. What I'm trying to say here is that rather than being negligible as such, the point is that these one have local anisotropies. Can you see these are pointing into specific directions? These ones are not shown because they're all uniaxial. They're all coming out of the plane that you see here. Okay, or plane, sorry, out or in. But it's just, and if they do tilt, they tilt all together. While these ones, they have a huge inertia, which we understand in terms of those big crystal field gaps. So we encoded in this simple Hamiltonian this type of anisotropy, and we studied the behavior of the magnetic features with respect to the competition with these two types of couplings. And even a Hamiltonian as simple as this can give us a good account of some of
May I ask a question?
Yes.
It's not just simple magnetization of those sublattices, but there is some frustration here, yes?
There can be frustration in this context of this material. I don't think that there is any frustration explicitly involved because it's known that they do order in a specific pattern. It's this so-called double umbrella structure that has been measured with neutrons. So what we did more recently, and it's the first time that I get involved explicitly in experiments, was using these scattering patterns, okay, to suggest that with this so-called REX, resonant elastic X-ray scattering, we could study the anisotropy of the terbium ions and so understand more precisely the details of these umbrella structures. So thanks for the question. I think it's a good moment to stop. I hope it's been interesting somehow. Thanks. Thanks for your participation.
Thank you, Bruno. Very nice talk. We have time for a few more questions. There are. Yes.
So just very naive, but you're dealing with those things that have a lot of electrons, like very large molecules, very large buffers, and like it looks to me like a scenario where you could maybe someone has already done something using spin density functional theory.
Yes,
They have done something.
I think so. Yeah. There is a lot of knowledge with density functional theory. What my take is that for their effective approach, they have. I'm not sure if they are not targeting that interest, but basically they are not taking into account interactions between the elements, which could be fully quantum mechanical. So what I was trying to convey with the first part of the talk is that even a single ion has actually a full dynamical Hilbert space that it can live in. And if you start to consider interactions in which you couple them via the oxygens, as we did with exchange, or via the ions, because they are strongly coupled, you could actually understand whether there is some actual quantum mechanics going on. So my interest comes a lot in terms of understanding how quantum mechanically at a small level, some, form of correlation, quantum correlation is likely to have an influence. Especially when you talk about spin waves. Spin waves are about this idea that these magnets are propagating in a certain way, and yet in most cases they take approximations in which these magnetic moments are basically free to rotate. If you forget about this quantum mechanics, then you either impose ad hoc that it has to be easing or that it has to be in a certain way, but you can't impose it out of the blue. If you understand what's going on behind, then you can possibly see if there are correlations between them, and so understand, for example, one of the aspects that we discussed is whether they are linearly polarized, whether some of these waves are propagated in a fancy way, and whether this could be, interesting.
I have one question left. Just out of curiosity, you mentioned lots of time correlations in the spin ice.
Yes.
And I wonder whether there are some data about the behavior of this correlation lengths with temperature or something like that. What is the
correlation between the monopoles?
What is the correlation, for example, with the compounds?
That's a good question.
Spin correlations, yes. What is the characteristic length? It's a few tetrahedra or 10 or I don't know.
I have to look at that into more details, I have to admit. As I said, it's also a subject that I haven't discussed in an interdisciplinary context, let me say, for a while. But to be honest with you, the thing is that they should be, because of the dipolar interactions, they should be long range. I wouldn't say surely not a few tetrahedra.
Okay, do we have any other questions?
Can I ask you guys a question for fun? Do you know who brought this deck of cards?
What is the?
There is a Solvay conference.
Oh yeah. This is a gift from China.
It's a very cute thing. I wanted to play a little game with you guys. About 1 minute.
Maybe it's better to go off.
Yeah, maybe you first go off.
1 minute. That's not the issue. I'm not going to be politically correct. No, my point is, I'll give you as two hints. Okay, you have Newton and Einstein as the jokers, which I thought was funny. No, my question is very simple. Who's the only one Sicilian in this deck of cards? If any one of you knows.
Sicilian? No.
Yes.
Majorana is.
No. So you have 3 attempts. 1 attempt is gone. I was thinking as well. I'm very shocked that Majorana is.
Was he actually Sicilian?
He was from Catania, which is my hometown. Fermi is from Rome.
Okay.
Who else? Pauli sounds Italian, but no Italian. Okay, so I thought,
But is he?
Archimedes. Archimedes was from theater. I'm sure you guys didn't know too. Because everyone thinks of him as Greek.
There was a
and he's
time
Greek.
when this was peaceful.
Exactly.
It was many things, but it was changing. Necessity was many things.
Yeah. That's it.
Okay. So